life-giving coffee. That's what you need after the party. I've always said that if you could take three things away, the internet would collapse instantly under its own weight. And those three things are TCP for congestion control, BGP for routing, and coffee for humans. So, thank you for making it here after the party last night. Did everybody go? Yep, I went. Was fun, but loud. I found it very loud. So, this is going to be a really interesting session we're going to go through today. Innovations in silicon and hardware, except it's not just about innovation in silicon, it's actually about, it's going to be about innovations in hardware, because we're actually going to expand the discussion beyond just silicon, although we are going to spend a fair bit of time talking about what Cisco is doing and innovating in silicon. Now, anybody who's seen me present before or during this week knows that there will be a picture of a rocket in my session because A, I like rockets, and B, I put a hashtag on the session called high bit rate, because we got a lot of material. Peter and I have a tremendous amount of material we're going to go through here in the next 90 minutes. Obligatory Cisco WebEx slide. Main thing to know about this, there is a WebEx Teams room that's open that you can interact with Peter and myself inside. Now, by way of introduction, my name is Dave Zaks. I'm a distinguished engineer with Cisco. Been with Cisco coming up on 26 years now. So inside Cisco, we live in dog years. So that's a little dog, 5 years per year, big dog, 7 years per year. So I've been with Cisco 125 to 175 years so far. It's starting to lose the hair to prove that. You see on the bottom of the slide some of the stuff I really care about, including some of the things we're going to spend a lot of time talking about today, which is flexible hardware and the impact that has for things like AI systems as we build them out. Joined today by my friend, partner, Peter Jones. Peter, you want to introduce yourself?
Not really, but I do want to point out that whatever Dave did, it was pretty bad because Cisco has not yet paroled him.
Yeah, that's right. I actually joined Cisco 26 years ago from coming to a Cisco Live. We used to call it networkers back in the day. It came to Vancouver a couple of years before I joined. I joined in '99. So a couple of years before that, networkers came to Vancouver. And I met so many cool engineers there, had such great discussions with them. It convinced me I had to come work for a company if that opportunity ever came up, which it did a couple of years later. And 26 years later, I still haven't found the exit door. Didn't introduce you, Peter. So Peter, joined today by Peter Jones. Peter is a distinguished engineer in our hardware team. I challenge you to ask him any question about the chips that we're going to talk about today that he can't answer. If you can do that, I will personally give you 75 cents.
Canadian or American?
American. We're in the US, Peter. So Peter does a tremendous amount of work at IEEE and is instrumental in establishing and guiding some of the standards that you see on Ethernet. He's heavily involved in that. So this is the agenda that we're going to go through today. I'm going to kind of kick it off, talk about how and why we create network silicon the way that we do. I'm going to hand over to Peter, who's going to talk about the flexibility in network silicon. One of the things, who went to the keynote on Tuesday? Do you remember them talking about this concept of flexibility on silicon, programmability? So we're going to drill down deep into that to help you understand what that means and what we do in that space. Peter's going to talk a lot about our networking silicon, latest ASICs and the platforms that we're building out of them. And then I'm going to come back at the end and talk about how we're using some of these things in AI systems. So that's what we're going to do today. So we drill through the agenda. Like I say, we have a tremendous amount of material to cover. So I found this statement several years ago that Chuck came out with. I kind of liked this statement that he put up there because I strongly believe that, but I'm actually going to take the liberty of correcting Chuck and saying that it's really about innovation in the network that's the most important part, because in the network, an ASIC silicon that we talk about is fundamental to everything we do in the technology stack. Everything we build on top of it that you see at the top, applications, Kubernetes, cloud infrastructure, all that kind of stuff, that's all great. Ultimately, all rests on hardware underneath. So we're going to drill into that hardware to understand what it is and what it does and why it's so cool. So we all know about the distinction between software and hardware. Of course, there's intermediate states like firmware as well. But the main thing that we're going to focus on today is hardware, and specifically on ASICs, application-specific integrated circuits, is primarily where we're going to focus. By the way, you notice I'm not sitting here reading the slides. I actually find it really annoying when I go to a presentation and a presenter reads the slides. So I'm going to talk about what's on the slides. If you see anything up there that you want to drill into, you want to talk about more, stick up your hand, ask a question. We'll absolutely stop and address whatever questions that you have. But I don't sit here and read slides. So We're going to be talking about ASICs today, ASIC silicon. So first thing to do when we start talking about silicon is we have to have a bit of a common taxonomy. We need to have a common language around silicon. So we're going to explore a little bit how we build silicon. So when we start off with a silicon chip, if we start off with a silicon chip like this one over here, this is about 19 billion transistors on this chip, 19.2 billion transistors on a chip. When we start off designing something out, it actually starts off with just a whiteboard discussion among engineers. What does a chip need to do? And we sit down and we analyze various things. We talk about R&D, what is the competition doing, what are technology trends, what's the state of the art of what's possible, what are the cost targets that we need to hit for a chip depending on the system that it's going into, what are the thermal and power constraints. All of that stuff gets munged together. And there's a competition here between marketing and engineering. Marketing asks for the moon, the sun, and the stars. Engineering says, I can give you the sun and the stars, but the moon is going to cost X amount more. And so there's give and take, but at the end of it, what you end up producing is what's called a PRD, a product requirements document. This is a spec for what the chip needs to be able to do. It's not the spec for how the chip's going to do it. It's a spec for what the chip needs to be able to do. Then you're going to take that product requirements document and you're going to take a look at all the different functionality that's inside it. And there's, of course, many different types of ASICs. When we think about ASICs today, we're going to be talking mainly about forwarding ASICs. But the fact is, in a platform, there are multiple different types of ASICs. There can be port ASICs, there can be forwarding ASICs, there can be buffers, all sorts of different things that can exist within a device. So once we've got that spec laid out, then it's time to actually start coding the chip. So I mentioned that this chip here has 19 billion transistors on it. Do you actually think that any human or team of humans lays out 19 billion transistors on a chip? I'm going to hand those around so you can take a look at that. It hasn't been possible to do that for many years. So a chip gets written as code. There's two common languages that are used in industry, Verilog and VHDL. Cisco uses Verilog. So that chip consists of 19 billion transistors. It's actually a couple of million lines of Verilog code that gets written. So the code, the hardware actually starts off as software. It literally gets written as code, and then it's run through a process called synthesis. The synthesis process takes that code and compiles it down into what's called a net list. The net list is typically a couple of gigabyte file. That's what we actually send off to a chip foundry, and that's what has the chip design. These languages are hardware description languages, so they have a concept not only of flow, like any language would have, but also timing in there. So basically what we're doing is we are constructing the gate constructs on the chip itself. Now, the next step after this is that we go through a process, called floor planning and placement. The chip is actually designed in functional blocks. So there'll be, for example, processing blocks, memory blocks, I/O blocks on a chip, all of which are kind of designed somewhat independently, interconnected and laid out. That's a bit of an art as well as a science, because anytime you have a rapidly varying electrical field, which is what you have in various portions of a chip, you also have a varying magnetic field at the same time, right? Electricity and magnetism are two aspects of the same fundamental force. Meaning that, for example, you can get EMI interference between one area of the chip and another area of the chip, which can impede its performance, but which is not obvious during the design stage. So floor planning and placement has to be done. Then after that, the chip gets sent out for fabrication. So fabrication consists of photomasking. Here we're showing that being done with a light source, being done on, imprinted onto a wafer. I actually have some of these wafers here. If I had half a brain on Thursday morning, I would have actually pulled these wafers out before, but I'll pull them out now. Bear with me a second.
How do you account for the EMI? Just plan directionality of that electrical flow? Or
yeah, or maybe separate, or the question is, how do you plan for the EMI, or how do you deal with any EMI effects that might appear? The answer, and I've got another wafer here too, Peter. So I'll pass these around so you can take a look at them.
Done.
Yeah, I got another one there too. I do want these back, by the way, and please be careful with them. They're a little fragile, and I wouldn't want you to break it and cut yourself. So functionally what you're taking a look at there is a silicon wafer, which is a wafer of an ultra-pure ingot of silicon. That ultra-pure ingot, we actually imprint the chip design onto it. It used to be using a light source, but the wavelength of light is too coarse for that now. So things that we're printing now are either done using deep ultraviolet or extreme ultraviolet. Anytime you go below about 7 nanometers in sizing, you go to extreme ultraviolet. Anything above that is typically deep ultraviolet. Extreme ultraviolet is kind of one step away from X-rays. So what you're doing here is you're literally burning the chip design into the wafer. That's not done on a single layer. It's done in multiple layers. How long do you think it takes to go from a blank silicon disk in a factory for an average chip? How many people have an iPhone 15 or 16 now? Yeah? If you got one of those, then you typically have like a 5 nanometer or 3 nanometer process node inside, or chip is designed with that kind of process node. That is the time from that wafer goes from silicon blank to a fully finished wafer in the factory is about how long, do you think? How long does it take to manufacture one of those? A week? More. More than that. About a month. It's about a month for any individual wafer to go from a blank to a finished wafer that's coming out of the end of the factory. So if the factory's producing, 20,000 or 50,000 or 100,000 wafers, those wafers are in there for a long time because they're printed in multiple layers. So what we're talking about here is transistors. Transistors is effectively on-off switches. So what we're talking about is how many of those we can pack onto a chip. The technology that we used for this for a long period of time is called MOSFET, metal oxide semiconductor field effect transistor, which is just an awesome acronym. You should go home and quiz your kids tonight on what a MOSFET is. When we went below about the 14 nanometer process node, anything below that, the industry actually switched over to FinFET. This was invented by Intel at the time, where basically you take a portion of transistor, you spin it on its side, and that gives you, and build it up in 3 dimensions, it gives you greater packing density. It's like moving from a single dwelling house to an apartment building, because now you can build things vertically on there. This was necessary once we went below about 14 nanometers in order to get greater packing density. The limits of FinFET have actually pretty much been reached now. So as we go down to about 3 nanometers and below, the industry is moving to a thing called a gate-all-around transistor, a GAA transistor, or what are called nanowires and nanoribbons. So what we're effectively doing is constructing gates. Now, it's a little-known fact that the entire technology industry, not just networking, is fundamentally built on 2 gate constructs. There's only 2 electrical gates that can be used as fundamental components to construct every other type of gate that we might want to use, and those are NAND gates and NOR gates. A not AND gate and a not OR gate, you can combine those in various combinations to make any logic circuit that you like. And the entire technology industry is based on that. Effectively, what we're doing here is we're packing millions, billions of those transistors together onto a single wafer. Who's ever heard of a company called Cerebras? Ever heard of Cerebras? Ever seen what they do? They produce a thing called the wafer scale engine. And what the wafer scale engine is, the entire wafer is one chip. If you took a look at that wafer I packed around, you can see all those little squares on there. Each one of those little squares is an individual chip, which will be cut out, packaged, and tested. In the case of Cerebras, the entire wafer is a chip. They have something like 4 trillion transistors on a single chip, which is a wafer. Right? Pretty amazing what can be done. So ASICs. Basically, when we take a look at ASICs have been shrinking for a long period of time. We all know that Moore's law says that approximately every 18 to 24 months, we double the amount of transistors can be packed onto the same piece of silicon. How many people think Moore's law is dead? That we've reached the end of Moore's law? They've been saying that for a long time, and yet we still manage to produce denser and denser and denser chips. There are physical limits to this. So Moore's law has slowed down, but it's not over. So why do we keep making denser and denser silicon? It really comes down to 3 things. Lowers the power consumption, higher performance, because the electrons have less distance to travel. Simplistically, you can look at it that way. And the one that's paradoxical is lower cost. As we move to a higher and higher and higher tech process node, we move from, you can just leave it there. We move from like a, let's say a 14 nanometer to a 10 nanometer to a 7 to a 5 to a 3 to a 2 nanometer process node. Making it smaller and smaller, it's more and more high tech. The cost should go up, no? But the cost goes down. Why is that? So that basically has to do with yield. So when you take a look at that silicon wafer, That's an ultra-pure disk of silicon, but there's various imperfections scattered at random over the surface of a wafer before you start manufacturing anything on it. Could be micro scratches, could be impurities in a wafer, and you don't know where they are until you manufacture something on top of them and then test to see if the actual resulting chip actually works or not. So this is called the yield. And so for example, if you took in a simplistic example here, every chip that is highlighted in yellow like that is bad because it's manufactured on top of a defect. In this case, my yield would be about 35%, or about 1/3, meaning that 1/3 of the chips would work and 2/3 of the chips would fail and have to be discarded after manufacturing. As I make the die size smaller and smaller and smaller, my chance of any individual die hitting that defect is less because the defects are where they are. The die is now smaller. The chance, if I shrink the die by 50%, I typically increase the yield substantially. In this case, I'm going up from maybe a 30% yield up to an over 70% yield, right? This is very important for silicon manufacturers. It's very important for anybody who's using silicon, because the yield is directly related to the cost. Obviously, you want the highest yield possible, right? So again, if you can shrink it more, you get higher and higher yields. So we've been shrinking silicon for a long period of time. This is a bit of a graph here showing from the early 70s up to modern day how far this has progressed, and we are not at the end of this progression yet by any means, right? So, fun fact, we put a person here. As long as you actually believe that we put a person there. If you don't think we did actually put a person on the moon, then we can have an interesting conversation afterwards. That's a beer conversation. But we put a person here using a thing called the Apollo Guidance Computer. The Apollo Guidance Computer consisted of 4,100 ICs, each of which contained a single 3-input NOR gate. In other words, we put a person on the moon using less than 10,000 transistors, but today it takes 19.2 billion transistors to route your packets, right? So we can do amazing things sometimes with not a lot of technology. The other interesting fact about that guidance computer, I told you I was a bit of a space geek. The other interesting thing about that Apollo guidance computer, it has less brains than your USB-C charger. Now, your USB-C charger has substantially more horsepower than the Apollo guidance computer had. So a thing that you're plugging into the wall to juice up your phone has more brains than the Apollo guidance computer, more storage, and substantially more processing power, hundreds of times more processing power. Again, pretty interesting what you can do when you have to do it with what you got in hand. So what we're talking about here is transistor sizing in nanometers. Now, nanometer is not a normal length that any human normally deals with. So in this case, what we're talking about here is maybe a bit of a perspective. A human hair, if you take a look at a single hair on your arm or off your head, that is about 100,000 nanometers in width, which maybe gives you some idea for scale on nanometers. But we can do a little bit better than that. If we take that single human hair, cut it in cross-section, so now I've got, I cut through that hair and make that as tall as the Empire State Building. Okay, so imagine a hair that was in cross-section as tall as the Empire State Building. On that scale, a red blood cell stretches up to about the 10th floor. A bacterium over here stretches up to about the 3rd floor. A piece of protein over here would be about the size of a small dog on a sidewalk next to that Empire State Building sized hair. And finally, we get to this little pinprick over here, which is the size of 3 pennies stacked end to end, and that is a nanometer, right? So imagine a hair, human hair cutting cross-section as tall as the Empire State Building. We're building things at a nanometer scale. If you don't think it's magic that we big squidgy bags of water called humans can build such things, and build them reliably, and build them repeatedly, and build them at mass scale, if you don't think that's magic, and I don't know how to explain magic. Okay, this is amazing, amazing technology to be able to do this. So current state of the art, typically most state-of-the-art chips today are considered to be in the 3 nanometer class. There's a company called Taiwan Semiconductor Manufacturing. If you haven't heard of them, they're one of the 10 most valuable companies in the world. TSMC manufactures about 90% of the chips in this class, right? 90% of the chips in the 5 nanometer to 3 nanometer class, which is typical state of the art today. The next step below that will be down to the 2 nanometer class. When we go here, and here you can see, for example, they're also building fabs in the US now. So they're going out and building fabs that will do N4 and N5. Those are 4 and 5 nanometer nodes, but I saw a recent announcement they're also going to do 3 nanometer in this fab. These are again, state-of-the-art buildings. To build one of these fabs costs an order of $10 billion or more. They're extremely expensive to build. And you can imagine you're building something at a 3 nanometer sizing. When you're dealing with tolerances that tight, even a car driving by on the road outside can introduce enough vibration into a building to upset the manufacturing process. You can imagine how sophisticated these buildings have to be. Question?
Is that still ASML technology?
I'm sorry, say again?
Is that still ASML technology?
Yes, so I'll talk about ASML in a minute. So the question was, what about ASML? ASML is a Dutch company. ASML is the only company in the world that actually manufactures the equipment that a company like TSMC would use to build chips at a 3 nanometer sizing. So we're going to talk about it, hold that thought, so we're going to talk about ASML in a second. So next step below this, we'll be going down to a 2 nanometer node. Once the industry goes below 2 nanometer, we will start measuring things in angstroms. An angstrom is 1/10 of a nanometer. So typically below this, we start measuring things in like an 18A or 14A process node, which is a 1.8 or 1.4 nanometer process. Question?
What's the size of a light? Aren't you going to get down to a point where you can't get any smaller? Because
Yeah, we will. So again, hold that thought. I've got a slide that talks about it. The question is, won't we get to a point where we can't make it any smaller? Yes, we will. There are physical limits. There's physical limits in lithography. There's also physical limits just in terms of the atomic structure of the devices, because we're getting down very close to atomic sizing. Yeah, question?
At this point, doesn't quantum tunneling become a problem between
Yes, the question is, doesn't quantum tunneling become a problem? So yes, it can. And again, hold that thought, because I'll talk about that in just a second. So one of the things we see here is that, again, by going to a lower and lower process node, we reduce power, we increase speed. That is the driver as to why we want to keep shrinking sizes. And typically, if you take a look at something that's mass manufactured, like smartphones, for example, you want to get the lowest power consumption possible, so you increase battery life, right? Obviously, we want more horsepower. So again, TSMC is driving towards 2 nanometer sizing, so is Intel. Intel is actually driving this down to the 1.8 nanometer or 1.4 nanometer process node. Intel, in their Oregon fab, is actually using a new version of the ASML machine called a high NA machine, high numerical aperture, which is required to manufacture things typically below 2 nanometer. They're the first fab anywhere in the world to actually get that machine from TSMC. It's a high NA machine that can manufacture with extreme ultraviolet lithography at this kind of process node. So as we go down below this, 1.8 and 1.4 nanometer, we have to go to a different type of manufacturing. We can't use MOSFET anymore. We can't use FinFET. We're actually having to go what they call ribbon FET, also called a gate all-around transistor. This is, again, required when we get down to these sizes. And the reason for that comes back to the thing that the gentleman back here mentioned. And I hate saying the gentleman. Sorry, what was your name, sir? Don. The thing that Don mentioned back here is to do with quantum tunneling. So one of the challenges we get as we go to smaller and smaller and smaller sizes here, I'm just going to click forward to that, is this concept of quantum tunneling. The question is, how low can we go? Well, a single atom of silicon is about 111 picometers wide, or about 0.1 nanometers wide. Right? So it's going to be hard to make anything smaller than an individual atom, but long before we get to that point, quantum tunneling effects will take over. So basically what quantum tunneling means, how many people understand quantum mechanics? Okay? It's one of the things that you both understand and don't understand at the same time, right? That's the whole point of quantum mechanics, is it's indeterminate. But the indeterminism in quantum mechanics means that simplistically, we think of atoms looking like that, where there's a little nucleus and there's electrons orbiting the nucleus like little planets orbiting the sun. It's not that at all, right? That's a mental model that we have, but that is not actually how atoms behave. Electrons work on a probability distribution. They have a high probability of existing in these particular shells, but there is a finite but small possibility that they could exist somewhere else. And so, for example, typically in our macro world, if I have two electrical carriers and a dielectric in between them that blocks the electricity from flowing, there's no electricity that's flowing from A to B. It's blocked by the dielectric in between. But at these very tiny sizes, if I have two wires running next to each other, there's a small but finite chance that an electron can actually tunnel through or leap over the barrier, actually appear on the other side of the barrier without going through the barrier, right? And that's called quantum tunneling. It leads to leakage current.
Dave, you might want to point out that for those who remember the physics, you actually work out where the holes are, not where the electrons are when you're doing the currents. You actually track the holes, which is truly bizarre.
Yeah, there's electrons and then there's holes. You're absolutely right. So that comes down also to type of semiconductor it's used. A type of semiconductor, we didn't mention that, but there's when you work out building transistors, there's called a PNP or NPN transistors, negative and positive. Some of them are biased to have electrons as a source. Some of them are biased to have holes, which are a lack of electrons. So basically what we're talking about here is, there are physical limits as to how small we can make things. There's also physical limits on how small we can image things onto the chip. Currently, if you take a look at one of these ASML machines, it's one of the most amazing machines that's manufactured anywhere, in my opinion. This is a picture of one of them here. This would be, a machine like this is about the size of a bus. If you ever see the complexity of it, it's absolutely amazing. It's almost 2 stories tall. When this is shipped out to a site, this would ship out in dozens of 747 freighter loads to a site. It takes months to assemble a site. Weighs about 180 tons and costs about $150 to $200 million. There's only one company in the world that makes the chips, or that makes a machine that makes the chips at 7 nanometer and below, which is ASML, a Dutch company. It used to be part of Philips. It spun out of Philips in the 1990s and is now one of the most valuable companies in the world because they have a corner on the market on this.
Other than silicon, is there any other material that are considered to be used to make
Yes. So the question is, other than silicon, is there any other material that can be used for this? There absolutely is, and that reminds me, I've actually got a chunk of silicon sitting in my bag here, so let me dig that out. Like I say, if I had half a brain, I would have taken these out before the session started. So the question is there any other material that can be used for silicon wafers? The answer is yes, there is. One that can be used is called gallium arsenide. I'm going to dig around for that once, yeah. I've got it in my bag somewhere. So there's another material that can be used called gallium arsenide. Gallium arsenide has different properties than silicon, but it's also a semiconductor. In other words, in some cases it can be a conductor, in some cases it can be an insulator. Gallium arsenide is often used in high power applications. So for example, if you take a look across the harbor here at the Navy ships that are running out there, the Navy ships are certainly going to have high-powered radars on them, and that is going to depend on, those are going to be done with gallium arsenide, the chips in there, because they have to tolerate extremely high amounts of emitted power.
The question is because the limit is 0.11 size, is there any semiconductor constellation that can help even the smaller size?
Well, there's various different things you can use for semiconductors. You could also use something like graphene. Under certain cases, graphene can also be a semiconductor. But silicon has a property is the positive properties is widely understood. We know how to manufacture on top of it. It's stable across a wide range of common temperatures that it's going to be exposed to. So it can get cold, it can get hot. And the industry has decades of manufacturing experience on top of it. So most other semiconductors that are out there are considered more exotic applications. Silicon is very much the mainstream that's being used. Okay, so ASICs, from definition to deployment, all the way from marketing requirement through architecture, through design, through synthesis, through floor planning. How long do you think that whole process takes? From the time that a bunch of engineers are sitting around looking at a whiteboard to the time you're actually holding a piece of silicon in your hand. How long? How many years?
3 years.
3 years? Could be. Could be as low as 12 to 18 months. Could be as much as 5 to 6 years. That particular chip that you see there that we're passing around is about a 5-year design time. And the reason for that is not because we were really slow on it. We did a bunch of really innovative things within that chip that we're going to talk about. So it also costs a lot of money to do this. Right? If you take a look at how much it costs to build an ASIC like that, it's typically north of $100 million investment to get your first chip back. There are very few companies that can make the investment to do this. Cisco is one of the only vertically integrated networking companies in the world, meaning that we do everything from soup to nuts, all the way from the ASIC design up to the fabrication of the entire system. Most other networking companies use merchant silicon from Broadcom or Marvell. The challenge with that is you don't control your destiny. So you take whatever the chip, which was designed by somebody else, can do, and you adapt to that, right? Because we manufacture everything on it, we design everything, we actually control what the chip can do. Okay, so why do we develop our own silicon in the first place? Really, from my point of view, there's a bunch of things around security and scalability and optimization, but it really comes down to flexibility and investment protection via this concept of programmability we talked about. Now, to explain a little bit what I mean by that, if you take a look at a traditional piece of networking silicon, it's fast, it's functional, but it's fixed in nature. In other words, you wrote that code at the beginning, you went off and wrote the Verilog code that forms the basis of a chip that was ultimately manufactured and burdened into silicon, and that's what the chip can do. So that original Verilog code you wrote might understand a V4 header, V6 header, MPLS header, GRE header, but then some other new header comes along or some new load balancing function is required, and the chip literally doesn't have the code and therefore the silicon to accomplish that. So that is the challenge, right? We see, these functions come along. For example, if we take a look at a chip like this, it is fixed, it has a fixed pipeline. Pull the packet in the front side, we take a look at it through a parser block, figure out what the packet is, we take a look at various different offsets in the packet, we run it through an ingress pipeline, through a whole bunch of lookup stages, we make a forwarding decision, we run it through an egress pipeline, make a whole bunch of egress decisions, maybe egress ACLs, egress QoS, et cetera, flexible net flow. And at the end of it, we do a rewrite on the packet because maybe we're going to rewrite the MAC address of the next hop, we're going to update that, we're going to maybe change some other things like DSCP or whatever the ACLs told us to do, and then we're going to forward the packet out. That's how our fixed ASICs and anybody's fixed ASICs work, fundamentally, right? There's usually a pipeline or a series of pipelines within the chip that accomplish exactly what we want to do. Now, it's very fast, it's very functional, but when new protocols and new functions come along, it's not flexible. Now, who in here keeps switches in your network for 5 years and then replaces them? Yeah, we love you guys. You guys are the best. We need more customers like you. How many people keep them for 7 years? 10 years? More than 10 years, be honest. Yeah? Yeah? A few people look back going, yeah, I keep for more than 10 years. So my point is that right now we're in the middle of this AI revolution. And that I really do think about what's happening in AI today, the same as what was happening in the early days of the internet. I've been working in networks since 1985, so this is my 40th year in networks. I got my first job in computers in 1979. So I've been doing this for a while, and where we're at right now with AI reminds me of the early days of the internet, right? It's that kind of inflection point. And that means that protocols, functions, capabilities are changing rapidly. New things are being invented, and we need silicon to adapt to that. Fixed silicon really doesn't meet the goal for that. So that's this concept of a programmable chip, a new code upgrade on a device, reboot the device, reflash the firmware into a chip, and now we've got a whole new set of capabilities in the exact same ASIC silicon. That's really the key that we want to be able to accomplish. Much faster in a CPU, much more capable than an FPGA. But you might say, well, hold on. I have these other things in a network. I have CPUs, I have FPGAs, I have network ASICs. What are the trade-offs between them? Because they all do come with trade-offs. So if we take a look at traditional CPU, like an Intel CPU, is very flexible. And it can actually do not too bad an amount of bandwidth. You can typically do maybe 10 or 20 gig of forwarding performance per core in the chip. So yeah, it's not bad. But CPUs by themselves aren't optimized at all for the things we do in networks. In networking, we're constantly doing table lookups. Everything's a table lookup, right? I'm looking up in a routing table. I'm looking up in an ACL. CPUs don't have any specialized hardware for any of that. So they have to be coded for it. There's a lot of inefficiency associated with that. So typically, if we take a look at the kind of cost performance curve on a CPU, it's extremely flexible. The cost is, CPUs tend to be somewhat expensive, and the performance is not great. If we take so typically what we're using CPUs for is control plane in devices. We use them to run the control plane. FPGAs, on the other hand, are great from a performance point of view. They give quite a bit of flexibility, but they're not great on cost. They're typically 10x the price per bit to move a bit through an FPGA as through a fixed network ASIC. We normally use FPGAs as gap fillers in devices. If I have a fixed forwarding ASIC that does almost everything that we want, but needs a few additional functions with it, then typically I might put an FPGA beside the fixed forwarding ASIC in order to add those additional, I need to handle one additional header or something like that. So we normally use them as gap fillers in devices, right? And usually only on lower volume devices because they're quite expensive. If I'm putting an FPGA as a major component into a switch and I'm going to manufacture millions of those switches, it's quite inefficient from a cost point of view. And then we have the traditional network ASIC, which we've used for years and years. Very cost effective, very high performance, lacks flexibility. This is really kind of the magic of programmable silicon, is balancing all three of these factors. And that's why Cisco saw this coming years and years ago. We didn't start doing programmable silicon with Silicon One. Silicon One is highly programmable, but we actually started doing this like 10 years earlier than Silicon One. One of our folks sitting here in the audience, Venkat Puella, worked a lot on the early days of our programmable chips. So that's why I was pleased to see Venkat coming into the session.
2006 is when I started.
What's that?
2006 is when I started.
And Peter started working on me even earlier than 2006, or even earlier in 2006. So Peter and I first met inside Cisco about 2010, 2011, something like that. I was a field engineer at the time, and I started working on this, with this switch that we hadn't shipped yet. We weren't going to ship until 2013, as it turned out. But when I understood what we were building in this first programmable chip, which is codenamed Doppler, so UADP, that's a chip that we were handing around. That's the heart of the Catalyst 9000 family. And before that, the 3850 and 3650, if you remember those switches. When I understood what we were building in this chip, my instinct as an engineer was to stand up and applaud. Because finally we were building something that balanced all of the factors. It gives me the performance, gives me flexibility at the same time, right? So that's really the key. So with that, I'm gonna hand over to Peter. And as you're coming up, Peter, I will answer a question.
What about GPUs over the balance?
Sorry, what about? What about GPUs? So GPUs are very specialized tiny compute engines that are massively scaled. So if you take a look at something like a GPU, like a Blackwell, or whatever the GPU of the day is, they are basically fairly simple compute engines that are highly optimized for doing certain things like matrix math, matrix multiplication, and you have thousands, tens of thousands of these cores packed into an ASIC. So they're massively parallelized, specialized processing engines. GPU is not appropriate for doing the kind of stuff we do of forwarding a packet. But they're very appropriate for doing things like, manipulating large language models. Question? What makes it a programmable ASIC? Peter is going to tell you chapter and verse on that. No, it's not an EEPROM. It's much more than that. That is an excellent setup question. I'm going to pay you 75 cents later for asking that question. Take it away, Peter.
Right, so everyone just take a breath, just have a relaxed moment, because Dave, when he starts talking, I don't think he actually breathes in the middle. Now, Dave, I am going to point out that you owe me about 7.5 minutes.
Yes.
And I intend to take my time.
All right.
So it's your problem at the end.
Okay.
And so, guys, thank you so much for showing up in the morning. A friend of ours, Tim Zaghetti, always used to do the morning quad session. And I used to think it was going to be a disaster because it would be so hard. But he made the point that anyone who showed up really wanted to be here. So again, thank you for coming and letting us talk to you, particularly Dan, because Dan is dressed really well. Oh, this is Dan, by the way. Dan makes networks inside tanks. So you want to have some fun, go and talk to him about what that means. I met another guy at the CCIE party who makes networks inside big drones, like the Predator type things. So there's the normal networks we mostly live with. So my friend over here from Ford with a hat, nice hat, he makes WAN networks. But I also know a bunch of his friends who actually work in cars. And what's interesting in the car, what it basically is an enterprise in Mini, because it's got a data center, access switching, and a WAN link. But it's just driving around. All right. So we've been building ASICs forever. Cisco is, we are actually the leading manufacturer of enterprise networking silicon, because we make our own and we sell it. So if people have used who used the 4500? Yes. 6500? Yes. Okay, so ASR 1000. So these are all things we built, and they had a whole bunch of different types of designs in them. So when I started on this program mid-2006 to became 3850, we sort of had a goal, because I used to work for DISBU, which was the 2K, 3K. We had this goal to go and do this thing because we saw coming really tunneling. We didn't know what it was. So we said, do we make the new thing faster? Do we make it better? It's like we made it flexible. Now, we also made it flexible enough for a design that we could scale it up to cover the entire campus. So on the way through, we obsoleted both the K architecture from 4500 and the Earl architecture. By the way, does anyone know what Earl actually stands for? It's an acronym.
What's that?
Earl.
Earl?
Yeah.
What does it stand for? EARL?
No, you can't answer.
You can't answer your Venkat.
Okay, so the answer is it's enhanced address recognition logic. And there's a whole backstory as to why that's like that. All right, so here, what we're seeing up here is, again, this is table scale and performance. So you're starting to see the Silicon One stuff up here. What you're seeing up here is the stuff that's really designed for web scalers and very high scale. What we're sort of talking about today really is A100 and the E/K100, which are in campus. Okay, so one of the things I was trying to figure out is how do I try and get to the commonality? Because in reality, the way these things are designed has a lot in common. So over this side, we have UADP or Doppler, and over this side is Silicon One. For every networking chip has a bunch of port interfaces. They get called different things. In our case, we call it the network interface. I'm hearing some echo from over there. Was that you?
No.
In the Silicon One case, they call this the interface group, or the ingress interface group and the egress. So next you have the packet process, which in Doppler we call a forwarding controller, in Silicon One they call an MPU. This is the thing which is actually looking at the packet and deciding what to do next. So it comprises a parser to take the packet apart. You then do a whole bunch of lookups. They can be forwarding lookups, they can be security lookups, you do filtering. You have queuing and buffering. And so if you look inside Silicon One, they call this a traffic manager. If you look inside Doppler, we call it the packet buffer and EQS and IQS. But they're doing the same function. You end up with a packet exchange. Now, in Doppler, that was based on a stack because we came from a stacking system. And that's fundamentally, it's a multicast stack bandwidth interface. If you look inside Silicon One, because they come from a different heritage, it's a fabric. So Silicon One really comes from people who are building very big distributed switches, whereas Doppler actually comes from people who are building 3750s. All right, we'll do programmable network ASICs. So you got the basic idea. The one thing we almost certainly know is we don't know what's coming next. So the job was, how can we actually do something which will give you security for a fair bit of time? So if, for instance, a friend up here who's at Ford, so let's imagine he's going to go and do a branch refresh. That stuff's got to hang out there for probably 5 to 7 to 8 years. Now, if he was building a facility for 1 year, I would say go and get the cheapest fixed switch you can get. But we have no idea what's coming in 5 to 8 years. So the goal with the programmable silicon is to let you say yes for more time. Because as soon as you say no, you become the barrier to progress. That's CATBIT, right? The denier of information technology.
Right.
Okay. So the idea is we need enough flexibility to basically pull packets apart. In this case, it's a very complex, particular fixed set of engines. It's actually got a whole bunch of TCAMs. It doesn't look anything like you'd think of a CPU. If you look forward, I have this long, flexible pipeline. So the pipeline basically carries a bunch of packet header fields and a bunch of interim results. Every stage actually launches 1 or 2 lookups. The lookups are 128 bits wide or 256. And we basically have it's very highly configurable logic to figure out what matters. So ahead of time, the chip doesn't know what an IPv4 packet is. It doesn't know what a V6 is. It doesn't know any of this stuff. This is all programmed. Now, when we were first doing this, we actually had one team that was going to go and build a compiler for this. And they called that Redshift, which made a whole lot of sense. Except for the fact that it was going away from you. We actually had another guy who actually went home over a weekend and basically wrote the basis of what became Blueshift, which became an application to do this. Flexible rewrites. We don't know what packet formats are going to be, so we have to actually build an engine that can rewrite different parts of the packet. And the thing which we really invested in was we knew tunneling was going to be interesting, so we put in a high-speed recirculation path. What that meant was when things like VXLAN came along, we could basically do functions on both the inside of the packet and the outside of the packet. And so that has become extremely useful. So for instance, when we first released 3850, we designed it for CapWAP. And this VXLAN thing came along and we just programmed it. And BGP, EVPN, the same deal. So we have enough flexibility in so we can mostly say yes, because that's what you want for your customer. You want to be able to, when they come up and say, can you do this? You say yes. Now, the trick about this is you spent more money on us 5 years ago, and the value to the business is now. So you sort of got to have the long-term view, which means you need to figure out a way to make sure the guy who signs the bills at the front gets credit at the end. All right, so UADP, the original one, as I said, is we first got silicon back in 2011. We actually shipped it in January 13. It's the same fundamental architecture. It started from, what was the original one? Like 480 gig, we're up to 1.6 T. Now, one of the things we found out was because we started really small, it was hard to grow further up, which is why we ended up buying a company called, I've forgotten their names.
Which company?
Silicon One guys.
Liba.
Liba. So we bought a company called Liba. The people in there had actually been at Marvell. Then they found a company called G Networks. They went into Broadcom, and then we bought them. We bought them because they had designed for a 10 terabit programmable chip. So whereas UADP grew from the bottom up, they grew from the top down. So they had better scalability ideas. The same thing, right? Flexible pipelines, so it's the same type of function, delivered a little differently. Common building blocks. We use x86, but not always, because we actually, one of the chips I have here is the one from the Catalyst 9200, and that actually has an embedded ARM cores. So sometimes we wrap the CPU in if it's a better cost optimization. Okay, so let's take a look at Doppler. So the funny story about UADP is ahead of time, we'd asked product management to come up with a good name. Because at the time, I think we just rebranded one of our chips to QFP, and we thought that was a really cool name because it was quantum flow processing. So I said, we want a good name. So unfortunately, they couldn't make up their minds. So the night before you went on stage, the VP at the time said, enough. I'm going to call this the Unified Access Data Plane, and the other thing the Unified Routing Data Plane. And we all sort of said, what? But Doppler was a better name. All right, so you guys, yeah, who had a 3850? Yes? My guess is everyone in the room, everyone's got everything. So what you're seeing is when we changed from like 6500 to 4500 and this, we tried to bring them more consistent. So one of the things I actually did was I was the software architect initially for the 3850. And if anyone used the 3750, you remember that the whole availability thing was sort of funny. It was distributed layer 2 and centralized layer 3. So we redesigned that architecture to be basically a virtual switch. Because we have, effectively run an active and a standby as virtual things. So that made it much easier to then progress off to these other systems. So we managed to take basically from the smallest thing down here all the way up. And so for me, that's been this is the crowning achievement of my life. So we released in 2013. We already talked earlier that refresh rate's about 7 years. We have more than half the market. So more than half the world's office facilities use my stuff to get their work done. Now, I would have liked to have 1% of the money, but that's a pretty cool thing to have achieved. Yeah, and by the way, if you guys didn't exist, it wouldn't matter. I actually moved to Cisco because I got sick of building stuff that disappeared, which happens in startups. Now, again, my friend from Ford, there is the companies that build 3 cars a year, and then there's companies that build all the cars a year. I want to be in that world. We're going to walk through this. I've actually told you most of this already. Network ports, we decided to put MACsec in hardware because we thought it was important. Forwarding controllers in the middle. So this is basically showing the big packet flow. Egress is on the same side. In the recirculation path, we actually put in packet reassembly and also encryption. Originally, the encryption was targeting DTLS for CapWAP. These days, it turns to throw in IPsec as well. If you look inside it, you've got a whole bunch of programmable stages. This is what you see here. There's stage 1, stage 2, stage N. The stages are all exactly the same. And then we basically, it's really very highly configurable, but we'll call it programmable. We can decide which stage is talking to which table for which content. Okay, so this is the evolution. You know, we first released this in 2013. I think I mentioned we actually got first silicon back in 2011. It was a very long development process, and I'm not sure today whether we would have managed to get away with that, but we had, our VP at the time was empowered to go do this. And so there was always, at the time, there was always a bit of an argument between ISPU, which was the 6K, GSPU, which was the 4K, and DSPU, which was the 2K, 3K. And we ended up winning. And so this has been the path, right? And what you've seen through here is a consistent value proposition. Scale changes, et cetera, but it's basically the goal was to deliver the same value prop. Right, so I'm not going to go through this. There's a whole bunch of numbers in here. Dave remembers the billions of transistor stuff. I really don't, because it doesn't matter so much. What I really care about is the function being offered at the right scale. Right, let's talk Silicon One. So as I said, Silicon One came in for an acquisition called the ABA quite a while ago now, and they were acquired because they had a design for a 10 terabit programmable chip. So their target is convergence without compromise. So they have a whole lot of designs. What they mostly do is their designs are structured so they're fairly easy blocks. So you might see a different chip number, but it's just basically the same design with multiple inside it. So as you see, it basically covers all the way over from high-end over to campus switching. If you've taken a look, you've seen the new 9610 and the new 389350. So they're the first Silicon One ones. There was some previous Silicon One stuff in campus, which had a bit of a bumpy introduction. This one will be much better. And remember, all these pictures are in the slides, so you don't necessarily need to take pictures. All right, so these are the ones you see. Q200 is the really high end, but basically K100, E100, and A100 are what you consider the core of the campus platforms. So this is where they're going to show up. As you see, basically we've got the 9500X, 9600X, which have already been out. The 9610. Has anyone gone to see the 9610 in WAST? What's interesting about that one is that we had to actually move from a PCB backplane to a cable backplane. We couldn't drive the channels far enough. And you go, but isn't the PCB better? And the answer is actually no. So if you ever get a chance, like pull the back of them up and take a look at the backplane. It's a lot of fun. All right, so I talked through some of this already. So the port interfaces over here. So this is what you call the interface group. Does all this port stuff, goes into the NPU. The NPU is pulling apart the packet. One of the things about the Silicon One receive NPU is it basically does both tunnel termination and inter-packet processing in the same pass, which is sort of cool. You come out to the queuing and scheduling. Depending on chip, you may have high bandwidth memory outside. That's where we basically package the memory in the package, which leads you to accelerate the memory. Did anyone used to have the 6500 Super XL? What they used to do with there is they would have an external memory chip. The problem with the external memory chips is they're very expensive in pins and power. So they basically now package it directly in, they put it directly into the package. On the outside, you basically have the same thing. TXMPU does egress policy, does rewrites, and it goes out the ports. Oh, okay, I talked through all of this. Okay, so central databases, there are a bunch of different ones. Now, so what happens, what becomes interesting is the path from what you see as a route to an entry in a database is complicated. So you have to think about these logically. So you've got the L2, L3. So you end up with all of the best match stuff, you end up with exact match, and you end up with policies. One of the things that's different about the A100KE is we've done a lot of enhancements on what's called, on the policy engine. So there's a whole bunch of stuff in here, I'm not going to read it through. Take a look later on, but the basic net is we've taken something designed for a very high scale, hyperscaler environment, which in general is very low feature, and we basically put the stuff back in you need for campus. So this was a bit of a learning experience for the Silicon One team, because we had to explain to them everything about what was valuable, because they came from a different background. And just offering what they offered to the hyperscalers would mean that Dan, or my friend from Ford over there, whose name I forget, would look at me and say, you must be nuts. So I talked a little bit about HCAM. It's an algorithmic hash-based TCAM. What it means is we do a whole lot of futzing, because TCAMs are very expensive in terms of area and power. So we basically combine TCAM with SRAM to do a whole lot of tricks. So it looks like a TCAM, but it really isn't. One of the things about this is it means that sometimes what you would expect in terms of entry count, like policy row to entry count, gets a bit funky. But it always used to anyway, because we used to do a whole lot of optimizations about how we laid this stuff in. A whole bunch of stuff on Silicon One. I'll get 9K. Guys, we're to 10. I'm on time. Mm-hmm. Okay, so here's where they are. I'm not going to go through this. You're going to see the same thing. There's ports, there's an ASIC, there's a backplane. All right, I'm going to take a second and a drink of water because I'm going to move topics. So, my role has really changed. I was for a long time, an architect inside building systems, and now I've really become an external role, and this is part of it. But I'm deeply embedded in the whole Ethernet standards. So I do that both working at 802.3, which is the working group for Ethernet, and I also do that I chair a group called the Ethernet Alliance. Now, the things about the Ethernet Alliance is we build some really cool content. So we have an Ethernet roadmap, because every product needs a roadmap. So what we try and do is capture the entire Ethernet ecosystem in a single bit of collateral. What's interesting about this is you can also actually download it and use all the pictures. So I encourage you. So I have some of these up here as well. So what's happening in Ethernet is our 10th anniversary roadmap. We have some fun, so it's back to the future, but you're seeing for the speeds, who's using them. Now, automation in this case, I'm mostly considering building industrial automation. The car guys are in there, but the way that people build networks in cars is a little specialised. It's actually more specialised than even my friend over here who builds tanks. So here's the speeds. So you're running through, and the speeds, what's sort of interesting is the speeds up here are getting up to 3.2 terabit. Now, I started working with Ethernet 10 megabits, so getting to 3.2T is nutty. And actually, my friend over here, Venkat, he currently works for Keysight and have a whole bunch of very interesting test gear, because although the industry is not there to those speeds, we need to test stuff years before we actually build the product. And so part of the Ethernet ecosystem is there's a whole bunch of people working together, and Venkat's one of the people. You want to know about the Keysight stuff? He'll tell you afterwards. I'll walk through all this. All right, technology. I first started working with Ethernet in 1986 maybe, when it was 10 megabit. What's amazing is the fact that the log scale, and we've gone like this. So the ability of the industry to basically provide continuous improvements at pretty common prices has been amazing. Form factors are changing all over the time. If you guys remember when we first came out with 100 gig, it was a very ugly form factor, I don't remember the name. But we sort of got to the stage where we end up with, in the campus, it's single lane and 4 lanes. This will be SFP and QSFP. But if you look at the higher speeds, they're now going single lane, 4 lane, 8 lane, which is where you start getting QSFP DD and OSFP coming in. And these images are all off the roadmap. I just borrow them. So signaling, when I first got involved in the optics side of the house, which was for 25 gig, I was amazed they used NRZ. NRZ is non-return to zero, and it's the simplest signal you can in the world. At the same time, 10G-base-T was using PAM16 with a Tomlinson Hashimoto precoder and an RS-FEC, because it was a much worse channel. So what actually happened when we went from 25 gig was the optics guys had to say, oh my God, my channel's not so good anymore. So the first thing they did was they went to PAM4, which is pulse amplitude modulation. So basically you encode 4 bits into a single byte time. Sorry, that's 4 bits into a baud time. But when they started looking further than that, they needed something better. So they came up, this is what's over here, they named it coherent. What actually is this QAM? But they had to come up with a better marketing name. So again, you're doing more and more work because you cannot run the channel any faster, which means we need more and more brains on the outside, which is why they get expensive in power. Question over here.
So we were using optics that are 16. Now we're moving from 6K to 64. Is it coming or is it?
So the gentleman's question, and sorry, your name was? Assad. So the question was, if you're at QAM 16 at the minute, you're going to move forward. And the answer is probably. It really depends when you have to. So this is always a balance between what the channel looks like and what you can do. If the channel was perfect, it will be really simple. So it becomes a balance of what you have to do. You might find that, you might find you have to do it for multi-mode, for instance. So I would say yes, I just don't know when. They're going to keep pushing the digital side because digital scales much better than analog does. So a couple of things have happened recently. Traditionally, we do fully retimed. So between the device, there'll be retimes in the modules. That's getting really expensive in terms of power. So where we're going is partly retimed. So LPO is linear pluggable, so there's no retimer. You can go see some of that in World of Solutions. There's LRO, which is partly retimed. Then you tend to go into onboard optics, which is CPO, and co-packaged optics. So co-packaged optics is when you actually put the optics in the package with the silicon. That's most optimized, but it's also most restricted. So I think LPO is going to be the way we go for a while, because it's the best balance of cost and performance. All right, I have a magic interface decoder. I'm not going to go through this. Again, this is a way to try and help you understand what's happening up there. If you go take a look, there's a whole lot of specs. Please take a look at this, download a copy, have fun with it. All right, so Ethernet Alliance, we do really three things. So the Ethernet value proposition is it just works. So we do behind closed doors interop between companies before they release product to make sure it just works. We show it off at shows with multi-vendors to show it just works, and we talk about it just working. So this was actually the demo we ran at OFC 25. I'm not going to go through it. What you're seeing is all the major people inside, including Keysight, and this is a collection of stuff that we had. So we want to go and show people stuff actually working, because then it provides trust. So that's what it looked like. It's pretty ugly, but this is the entire industry working to make sure it just works when it gets to you. So this is sort of invaluable, because what you don't want to have is mine works with mine, and his works with his, don't work together. Our job is to make it work together. Okay, speeds. This is from my friends at Deloro. This is their predictions. 2029, the bulk of the market is still 1 gig. And this is enterprise switch ports. So you have to take a little bit of a grain of salt of people telling you everything's going to go faster. So to actually get anything useful, I'm going to take out everything and everything. So what you're seeing is 2.5 and 5 are growing in the campus. And in the data center, it's 800. Yes, sir?
Yeah, but in the core networks, people like us demanding 400, 800, so.
Sure. But this is...
Repeat the question, Peter.
Sorry, the question is, aren't the core networks demanding higher speed? Yes, but the volume is enterprise campus. And so this is percentage of ports in 2029. But the thing becomes is most people go, oh, everything must be 25 gig. The answer is no. We're still dominated by 1 gig at the campus. So I'll drop this out, and you see the growth at 2.5 and 5, and you see growth at 800, which is sort of where you're asking. But it's not the long-haul people that's growing. So now I'm going to take a look at the ISP trends, and this is from a different group called 650. So their projections, what I have here is both ports and revenue. So 2029, they're saying almost everything is going to be 3.2T. That doesn't exist yet, and that's really scary, because they're expecting this to come in really soon. They're saying they think 3.2T's got to ramp by 2027. That's not very far away. So this is the entire AI network, back end and front end. If you look at the back end by itself, which is a scale-out network, it's even further. So they're saying by 2029, 75% of the revenue is going to be 3.2T and probably about 60% of the ports. Let's let that sink in for a minute. So the trick is we've been going faster all the time. We have to meet the market needs. We don't know how to do some of this stuff now. So there's a project going in 8.3 at the minute to do up to 1.6T. We don't quite know how we're going to get to 3.2, but that's what technology evaluation is for. The trick is the cadence just keeps going up. Power has become a key problem, and so we're doing all sorts of things to try and figure out how power works. If you look inside the systems, they're going higher and higher power. And basically, so the power increase isn't as much as you think, but it's becoming a critical constraining factor. So there's a sort of reach off here. There's a trade-off about what you can do. You know, the within rack stuff is the easiest and cheapest. As soon as you move between racks, it gets more complicated. And again, it's always the question of what can I do for what price at what scale. LPO and LRO basically take out, they're still pluggables, but they take out some of the DSP stuff, so they're best choices. Go take a look. We have some LPO stuff down in WAS. Okay, so liquid cooling is becoming a thing. So the NVL72 is 120 kilowatts per rack. Kilowatts. But Google's actually planning for racks up to 1 megawatt. So just think about the power density and cooling you have there. So Meta and Microsoft have a Mount Diablo design for power supplies that they're going to put into OCP. They're going to put 400 volt DC directly into the rack. Just efficiency. So these numbers are just amazing. So how do you cool those things? So cold plate cooling. So you basically put a humongous copper plate on top of the ASIC, and you basically run cold liquid into it and warm liquid out. because the fluid is just so much more effective as a power transfer. What it actually becomes is you don't only save money from fans, you actually significantly save from chiller costs, because now I don't need to have the air in that place really small, because I'm running an external heat exchanger. You can go down and see this on WAS. A friend of mine helped design this. It dramatically changes power unit effectiveness, which is how they measure. And that's really trying to figure out of the entire power consumption of the DC, how much is going to the IT stuff versus overhead. So you'll find Google and other people, they publish these numbers and they really care. So this is what it actually looks like. It's sort of fun. It's complicated, particularly to make sure the thing becomes leak-proof. We cool the important stuff. So there's a big cold plate on the CPU here, but we also run a cold plate through the middle of the optics. Because the goal is how do we get heat out of these things? So liquid cooling is taking about 80% of the heat. And that just simplifies our design enormously. All right, co-packaged optics we showed up at OFC 23. Has anyone ever been to OFC? Okay, so it's an optics conference. We tend to show off things behind closed doors. So retimed optics at this stage was 1,240 watts in this system, and CPO was 971. So it's a way to reduce a lot of power. We did a similar thing this year with 51C linear pluggables, and that took 700 watts of power out. So if we can take this power out of the system, it becomes much more deployable. It really reduces your infrastructure costs. All right, there's a thing called fault managed power, otherwise known as class 4 power. It went in the National Electrical Code recently. And what it actually is it's touch safe high voltage DC. So you guys are familiar that PoE is a cool thing because it's touch safe, it's very easy to deploy, it doesn't need conduit. But it can't carry that much power. So fault managed power carries a lot of power, up to a kilometre maybe, 600 watts. There's a yield compliance check for this. And the whole idea is that one of my friends who's been involved with this for a long time, he will do the test, he'll put it on his tongue. Because basically what we do is we send a waveform and we pulse the power, then we check for a short. And we can catch the short fast enough that it doesn't hurt people. Cisco has a collaboration with Panduit to do some of this. You can go see it in WAS. This is a way to deliver a lot of power over quite a long reach that's touch safe. So again, you can think about the difference in terms of deployments, what you can do. So, my friend here, you might find this useful in a tank for a whole lot of reasons. I'm actually on time. It's you.
You're ahead of time, Peter.
I have one question.
You made
Only one question.
So you're talking about PoE power. A lot of with the big name cloud service providers are looking at fully submerged cooling. For example, Microsoft had a program where they stuck everything in a tank and put it in the ocean. Is that anything that you guys are entertaining for design?
So the question is cold plate design versus full immersion. I've seen a bunch of full immersion stuff. It's very cool. I think this is the difference between doing Ferraris and Formula One cars. I think immersion is what you do when you have to. It's quite complicated, that the material is sort of nasty. So I think the general rule becomes you do air if you can, you do cold plates if you can't do air, and you do immersion if you can't do a cold plate. Because you can imagine the serviceability issues with this, right? This is complicated. So I think immersion cooling is going to be one of those things we'll always need for the bleeding edge. That make sense?
All right.
Data centers in Antarctica.
Data centers.
Actually, I want to go back. So Dan made the point. A lot of it actually matters where you are. Because one of the things you do, if you put a data center in Finland, things get lots easier. We seem to want to put them in Arizona with no water, which I think is nuts. So I would say I have a session on Ethernet for AI, which covers some of this. We have a layer -1 problem. We need land, we need power, we need water, and we need construction workers. So those things are some really interesting physical problems to solve. But yes, if you locate your data center, for instance, in British Columbia, where David's from, power is cheap. So where you locate makes a huge difference to your actual operational cost.
All right, so we proved a couple of things so far in this session. One is that we have more acronyms and trees than kids in a treehouse. Every time you turn around in networking, there's more acronyms and more acronyms and more acronyms. TCAMs, HCAMs, everything. The other thing is, can you imagine, even though we're going to talk about AI coming up here in the next section, can you imagine the complexity of trying to build a machine that could talk about all the things that we've talked about so far in this session for the last 60 minutes, that's powered only by a muffin, right? I ate a muffin on the way here as I was walking down the corridor, right? Put a muffin in the top of a machine and it talks about silicon for the next 60 minutes, right? That would be a complicated machine to build. It took nature 4.5 billion years to build that machine. So, AI/ML, what are we using all this stuff for? AI encompasses many things. It encompasses everything from machine learning, deep learning, all the way up to generative AI, which of course is what set the industry on fire in the last couple of years, because we've moved from a very deterministic algorithmic approach to something that's much more based on patterns, learning, and self-improvement, right? This requires the movement of massive amounts of data. If you're gonna have a system that learns and improves on itself, it just stands to reason that we're moving a lot of data around that system as we're building out these neural networks that have multiple layers in them. So for example, how many people have heard of Llama as a model? Played around with Llama? Downloaded Llama and started playing with it? You just go to ollama.com, and as long as it's compliant with your security policies of your company, you can install Llama and start using these LLMs locally on your laptop in about 3 minutes, right? It's very, very easy to do. Basically, when you're working with these type of models, there are multiple layer models. There's an input layer, there's an output layer, and there's multiple hidden layers in between. So some models could be 16 layer model, 32, even 64 hidden layer models that are sitting in between. But one of the things we can, if we back out to like the 100,000 foot level, we could ask ourselves, why is all this stuff with AI happening now? Why wasn't it happening 5 years ago? Why isn't it happening 2 years from now? Why now? And to me, it fundamentally comes down to one word, which is scale. These type of systems have been built in academia for years. Jeffrey Hinton actually won the Nobel Prize in AI, first Nobel Prize ever in AI last year. And so fundamentally what they've built out in academia for many, many years is the concept of neural networks, right? So when we take a look at a neural network, it really consists of two things. There's an artificial neuron called a perceptron, and a thing called comparable to synapses in the human brain, connecting those neurons called parameters. Parameter instantiates out into a model as a number. So if the model that you're looking at is quantized as 16-bit, that'll be a 16-bit number or a 2-byte number. So if you take, like, say, a 70 billion parameter LLM, which would be a mid-sized LLM today, that's quantized at 16-bit, that 70 billion parameter LLM would be about a 140 gigabyte file on disk, and 140 gigabytes that needs to fit into memory or high bandwidth memory. So one of the things we typically see today is that these large, mid-sized to large models cannot fit inside a single GPU. It's not just about training the model, it's about using the model even for inferencing if you're gonna do that locally. There's a lot of reasons why you wanna run these type of models locally on your device, on your premises, from a security point of view, privacy point of view. You may have corporate data you're gonna feed into a model, you're just not allowed to put it out into a cloud-based model. But these mid-sized to larger models are not gonna fit into a single GPU. We have to split them out across multiple GPUs in a network, and then of course the network becomes very critical for integrating them. A demo that we did in another session earlier this week, at a session called AI/ML for Network Engineers, which you can look up in the on-demand catalog. What we did in that was we took a 70 billion parameter model, split it across 8 different GPUs, running in a couple of different servers, interconnected with a 10 gigabit network on the back end, and then typed in, write me a 100-word poem about pirates. How much bandwidth do you think it took to spit out 100 words on the front end? How much bandwidth do you think it took on the back end in the data center? Where did it peak at, do you think? How much?
1.2 terabytes.
Not terabits, but it peaked out about 7 gigabits per second to write a 100-word poem. On the front end, you as a user, 7 gigabits per second on the back-end network, because the model is distributed across multiple hosts. These workloads that we have for hosting these type of neural network models in a data center don't look like any other kind of workload you've ever seen before. And that's for one user. Imagine if you're implementing this for a company where you have thousands of users on there, right? The bandwidths go through the roof. So effectively what we're talking about here is building out these artificial neural networks. This is where GPUs have really come into fore because GPUs are really, really good at doing matrix manipulation and matrix multiplication. To NVIDIA's credit, this wasn't, they didn't actually invent the GPU for this. It was invented for gaming. But it just turns out the kinds of things you need to do for gaming are exactly the kinds of things you need to do for manipulating these AI models, right? So that's why NVIDIA is one of the most valuable companies on the planet now. The other thing that came in, this was a paper that was written in 2017, which was a foundation for the transformer model. The attention is all you need paper that's written by a bunch of researchers at Google, as well as some folks at University of Toronto. And basically what this introduces is the concept of multi-head attention blocks and feed-forward networks. These are effectively the heart of every large language model that's being used now in diffusion models. It's the concept of a transformer architecture. So what do I mean by that? If I put up this sentence that says, I swam across the river to get to the other bank, as human beings, we look at that and we instinctively know that bank in this context means riverbank. It doesn't mean bank where you put your money, but that's because the word bank occurs in the context of swam, and river in this sentence. This is exactly how large language models work. It's on the basis of a context window. So basically all LLMs, what they fundamentally are is word prediction engines. I'm predicting the word that comes next based on the words that preceded it. And so that the number of words I'm able to look back at is called the context window. Initially, when these LLMs came out, the context windows were pretty small, maybe 2K or 4K tokens. A token is roughly equivalent to a word, or a fraction of a word. But now the size of these context windows, 128K, 256K, 512K, so they can basically span, books worth of text in terms of writing what comes next. That's what's made these LLMs more and more capable. This, fundamentally, is what moves large language models from a syntactical understanding of language. Your spell checker understands the syntax of language. This moves us from a syntactical understanding to a contextual understanding. So this has caused a Cambrian explosion of models. I'm not sure if you know what I mean by who knows what I mean by Cambrian explosion? Good. A lot of people know their evolution, right? So 650 million years ago or so, life went from a small variety of simple forms to a huge variety of forms, not all of which persisted and lived through in the evolutionary process, but life proliferated into a large number of forms. That's what's happened with models. We see both closed source models, or if you go off to a site like Hugging Face now, you will see north of 1 million open source models on Hugging Face. So you can freely go in and download. They have leaderboards so you can find the right one. But there are massive numbers of open source models now as well. And these models have moved from having billions of parameters to having trillions of parameters. Remember, a parameter is the connection between the weighting between artificial neurons. When the LLM is trained, what you're effectively doing as you're running through round after round after round after round of training is tuning the weights between the artificial neurons, which helps them or allows them to do the word prediction that an LLM does. Now, fun fact, human brain has about 86 billion neurons in it that we all carry around inside our heads. Based on the humans that I've interacted with over years, I would say that some humans seem to have more neurons in their head and some seem to have less, or at least to use less. But between those 86 billion neurons, there's about 100 trillion synaptic connections. So we're not at the complexity in LLMs yet of the human brain, but we're rapidly approaching it, and probably within the next few years we'll surpass it, right? Which is amazing. Again, you talk about silicon being amazing to build. These are the systems we're building with silicon, equally amazing, right? So how are LLMs trained? It's really a 4-step process: data collection, tokenization, parameter learning, and fine-tuning. So to explain those maybe a little bit more detail, data collection, we're training on the corpus of the data, which could be the entire internet, or it could be more specialized. So for example, if you attended the keynote on Tuesday, you heard us talk about a deep network model that Cisco's developed. We've trained it on network-specific data. You could equally have things that are trained for doing coding, that are trained for security, that are trained for whatever, right? And a lot of different models that you see out there on the site, like Hugging Face, are trained in a specific way. Then we do tokenization and parameter learning, where we basically break the data down into tokens. And what we're doing is locating those tokens in an n-dimensional space. As humans, we can't visualize anything more than 3 dimensions. The typical number of dimensions that's used for a model could be 800 to 1200 dimensions, maybe even more. We're saying this word, let's say king, occurs in this word, in correlation to this word, let's say queen, more than it occurs in relation to another word like table, right? So that allows us to basically relate the words to each other in this very high number of dimensions, and those are all represented as numerical vectors. Then the numerical, what we're doing at that point is training the model to fine tune on the information that has been learned on. So how does this matter for silicon? Fundamentally, what we're doing with these AI systems is they go through 3 steps. The model needs to be trained. For a typical frontier model now, like Claude or GPT-4 or what have you, this training process takes months, running through thousands, many thousands of rounds of operation to train the model. Then there's a validation process, which typically involves humans, where we're validating the output of the model and we're taking bias and other undesirable artifacts out of the model. And then finally, there's a use of the model, which is inferencing. So if you go off to a site like Olama, download models, run them on your laptop, you're doing inferencing. You're using the model. The important part is all 3 of these stages involve moving large amounts of data around. This is why the network is fundamentally important as we're dealing with these AI models. Now, I mentioned before that what AI looks like to me today is it looks like the early days of the internet. I think that's where we are. Back in, I got my first job in networking, I mentioned in 1985. In the early 90s, you started to see the internet really start to proliferate, and then it hit an inflection point, which was the first web browser. Anybody remember NCSA Mosaic? First web browser that came out? That was the inflection point. That's where the internet took off, because all of a sudden you didn't have to know Gopher and FTP and all these different things. You just had to know how to click on something. Kind of like ChatGPT, right? You don't have to know anything about how the neural network models work. All you have to know is how to type a question. And all of a sudden you get this magical seeming answer that comes out of it, and the technology proliferates. But getting that answer, and getting that answer rapidly, requires a network, requires an appropriate network. So what we're talking about here is time to first token. That's a common measurement of performance of these large language models. We want to optimize the network to give us as rapid inference as possible. So what we're doing today when we're building out these type of networks, the front end of the network is built the same way you've always built a data center for the last 10 years. Then over here, what we're building now is a scale-out network on the back end, strictly for interconnecting the GPUs. Right? That back end network doesn't connect to the outside world, strictly for interconnecting the GPUs and doing this in as close to a lossless fashion as we can get. Now the reason for that is because we need these systems not to drop packets. One of the challenges is if in that backend network, it drops a packet, all the GPUs after each round of training need to synchronize their data with each other. If I drop packets, yeah, they'll get retransmitted and they'll get there eventually, but that means 99% of my GPUs, which got the data, have to wait for the 1% of GPUs over here where we dropped a few packets on them. That's called a barrier operation. It slows everything down massively. So one of the things we need to do on these backend networks is build them out in such a way that we don't drop traffic in them. The technology we use for doing that today is called DCQCN, Data Center Quantized Congestion Notification, which is a combination of 2 factors, explicit congestion notification and priority flow control. That's kind of the way that we do it today. The protocol we use there is called RDMA over Converged Ethernet, RoCE. We actually use RoCE version 2, which is routable. The original RoCE was only a layer 2 protocol. But fundamentally what we're doing is large memory transfers from GPU to GPU, bypassing the kernel, basically going direct from memory to the NIC, over the wire to the NIC to memory. So we bypass everything in the system to get the most rapid memory-to-memory transfer we can get in a GPU, but it's still got to go over the wire. And so we need to optimize how it goes over the wire. In traditional Ethernet, I'm doing congestion management using equal cost multipath. Everybody knows how ECMP works, right? It's one of the joys of coming to a networking conference is you can mention a function like ECMP and everybody in a room knows how it works, right? We're basically hashing the 5-tuple on the packet, source IP, dest IP, source port, dest port, and protocol to a smaller value, and then based on that smaller value, we're picking the link that we're gonna send it over that's equal cost. Fantastic, that works great for your average, normal, non-AI workload. The problem in these AI workloads in the backend network is there's almost no entropy. in them. There's almost everything is going from one IPN port on one given host to another IPN port, another given host. It's all going to hash. That might be gigabytes of data that's getting transferred with this memory-to-memory transfer, but it's all going to hash onto one link. And then maybe another one just happens to hash onto the same link. Now I've got a congestion or hotspot, but I've got other links that are underutilized. So ECMP is not a good match for doing this type of flow control or congestion avoidance that we want in congestion management. We have enhanced Ethernet, where we can do things like flowlet switching. We can do spraying and reordering in a smart NIC. What the industry is trending towards is scheduled Ethernet and Ultra Ethernet. Ultra Ethernet is actually a new consortium that's fired up. We can debate the merits and non-merits of Ultra Ethernet and the kinds of things they're doing, or whether it's smart on what they're doing. But the fact is that the industry is working to build these networks in a more intelligent way on the back end to avoid hotspots, to avoid congestion, and to increase throughput. Absolutely required for building out networks to support these AI/ML workloads. That's some of the stuff that we're building in the chip. That's why when our execs stand on stage and say, hey, programmability is important in the ASIC, because has the industry landed yet on the right way to do this, the best way to do this? No, they have not. This is a work in progress. And that means that you don't want to have functions that are burned into silicon, that that's all your silicon can do. Because then when the industry lands on the thing that we're going to ultimately all agree on for as the best way to do congestion control, congestion management, load balancing in this environment, you don't want to have to go out and replace millions of dollars worth of network here. Right? You want to be able to use programmability to upgrade it in place. That's really the key. Okay, so performance here, the performance of this depends on the traffic characteristics. Performance of these ones over here in these last two columns does not depend on traffic characteristics. So Cisco's AI strategy overall: detect and connect, protect and connect everything that we do. One of the areas that I'm heavily involved with is called Hypershield. How many people heard of Hypershield? Be pretty amazed if you go to a show and not hear Hypershield somewhere. Hypershield is basically a highly distributed security firewall that we are distributing across multiple devices in the network. It's a pretty cool project. I've been involved with it now for about a year. Basically what we're doing is we're allowing you to author policy and then implement that policy both in network-based, host-based capability. How many people have heard of eBPF? Extended Berkeley Packet Filter. It's an awesome capability that basically we build it, it's built into the Linux kernel. It allows us to make the Linux kernel programmable in a safe way so that we can pull telemetry out of the kernel and also implement security controls in the kernel. So for example, when we're authoring policies with Hypershield in a centralized way, we can push those policies down to be enforced on a VM or on a container. We can also do that on the switch itself. So we can push this, we have a new version of the Nexus switch that over here has 4 AMD DPUs in it, data processing units. So these are accelerated compute engines that are optimized for doing network-related tasks. That gives us, with 4 of those in there, that gives us about 800 gigabits per second of highly programmable silicon that we can use for doing things like implementing local security policies. By the way, the language that we program both those AMD DPUs in and also Silicon One is called P4. Stands for Programming Protocol Independent Packet Processors, which again is just an awesome acronym. Came out of Stanford. It's a standardized way to write code on these type of programmable chips. Silicon One implements it. These AMD DPUs implement it. We also are introducing over the next couple of months, and again, you saw our execs talk about this in the keynote, we're introducing some additional Nexus switches with additional DPUs. We're also introducing a security coprocessor to run alongside Silicon One down in something like Catalyst 9350 running in the campus. Our goal is to get this level, not just of programmability, we've already got that, but to get this level of security functionality, integrated security functionality into the fabric and network deployed as widely as possible, not just in a data center, but deployed out into campus as well. Now this will be an ongoing story over a period of time. So we come back here with this session next year. We are going to have a lot more to say about what we're actually doing with this capability. We've just announced the hardware to support it. It's pretty interesting. So with Hypershield, we go after multiple use cases. One of the interesting ones here, I think, is distributed exploit protection. So we talk about these AI systems. AI systems are always used by the good guys, right? AI systems today are widely used by hackers where an exploit is announced. They will feed the details of the exploit into an LLM, and the LLM will tell the hacker within a few minutes how to go attack or exploit, that particular vulnerability that was announced. If the hackers have those type of tools, and we have to make sure that the good guys have those tools as well. So that's one of the things we do in Hypershield is we not only have the ability to generate not so much a patch, but what we call a compensating control in real time, what we call a shield. That shield can then be pushed down, that compensating control could then be pushed down to eBPF, let's say running in a host or into a network enforcer, so that you haven't actually patched the code. The code on your device still has a vulnerability in it, but we prevent the vulnerability from being taken advantage of. That's fundamentally what we do with the distributed exploit protection Hypershield, and it's pretty cool. So we use AI in a bunch of different ways in Hypershield. One of the other things that I think, the last thing I'll talk about with Hypershield, I get pretty excited when I talk about this stuff, but last thing over there is this concept of a digital twin. One of the things that we do in those DPU-based switches is we actually run 2 data planes inside it. We have what we call an active data plane and a shadow data plane. When a packet comes into the DPU complex, we replicate the packet, we send it down the active data plane and the shadow data plane. How many people in here have ever done an own goal when you implement a policy, a new policy, QoS policy, security policy or something, into a network and you break something? Yeah, every network engineer has done that at some point. You push a policy in and it goes sideways, you break something. So wouldn't it be cool if you had an active and shadow data plane that you could push the new policy into the device, packet comes in, gets replicated, goes down both paths, but it only gets forwarded out of the active data plane with your old policy, but it also goes down a shadow data plane with the new policy, and you can see exactly, would it have matched it? What would it have done? And then at the end of the shadow data plane, we just drop it, right? And then you can just flip a bit to change active to shadow, shadow to active. Question?
So with Hypershield, are you talking about applying this policy at, from going up a couple levels here like that? But like at the port level, or are you talking at like the VLAN level? Like where is that?
That's a very good question. So the question is, in Hypershield, where is the policy defined? Right now, today, with the current implementation, we take the VLAN, we do it at the VLAN level. So you take a given VLAN and you say all the traffic in this VLAN is going to be processed not in the ASIC like Silicon One, it's going to be processed in DPU. That's why we have 800 gigs worth of performance, and then you condition which VLANs are going to go into DPU complex and be processed by policies and protected by Hypershield, and which ones are just going to be forwarded normally in ASIC. Does that make sense?
Yeah, that's exactly.
We could do it another way, but that's currently the way we do it. What we tend to do is we implement kind of the simplest thing first, and then over time we could get more sophisticated in how we do traffic selection. Today, the traffic selection going to DPU complex is based on VLAN.
Well, that's great. I have a use case right now that'll be perfect.
Perfect, awesome. So other things you're seeing across company, of course, is all the things we're doing with assistants. All the way across the board, everything has an assistant. I think it's important, though, to differentiate between what is an assistant and what is an agent, because people throw these terms around interchangeably, and they are not, in my opinion, interchangeable. So if I take a friend of mine who I'm presenting you with this week, I put his picture up there and put sunglasses on him, and pretend he's a famous Hollywood actor. If he was a famous Hollywood actor, he would certainly have an assistant, and he would task that assistant with doing certain things, right? Do my expenses, run some errands for me, et cetera, et cetera. That is what assistants do today. If you take a look at an assistant in Catalyst Center or Security Cloud, whatever it is, right? That assistant is going to be narrowly tasked on a specific set of things. Not to say it's not valuable. It's very valuable, but it's only tasked to do certain things. Very different than an agent. An agent would be something like this, where the Hollywood actor would come along and say, get me a part in the next big Hollywood movie. Then the agent leverages the various different tools and functions that are available to it, including iterative reasoning over tasks, accessing outside tools, and accomplishing that task and then reporting back. To me, that's fundamentally the difference between an agent and an assistant. Now, it is a bit of a fuzzy line in between, because you say, well, what if I have an assistant calling another assistant? Is that assistant now an agent? Well, kind of. It's doing agentic things, right? But to take a simple assistant and suddenly start calling that an agent when it's not doing anything that an agent would do is a bit disingenuous, in my opinion, right? So I like to differentiate between them. So tools and function calling and memory are some of the key characteristics. You can see that one of the things that we're doing as a company is unifying our assistants across the board such that what you'll be able to do there is talk to any one assistant. Like let's say your firewall assistant. Say I've got a performance issue with my firewall. It knows that I've got a skills repository. It can go out and talk to, let's say, Thousand Eyes, run a Thousand Eyes test across the firewall and actually be measuring the performance across it. Without, in other words, you don't have to swivel chair from assistant to assistant to assistant. We want to unify the assistants together so they can call each other and know what each other can do. That's the first step on the way to agentic AI, if you think about it that way. Okay. If you want to know more about it, you can go to a session my friend Richard Jang did on Tuesday. Awesome session. He goes into agents and assistants until your eyes bleed. This is he goes into that in extreme depth. The very last thing I'm going to talk about is quantum, because Cisco did do some interesting announcements in quantum recently. We all know the difference, I think, between classic problem solving and quantum problem solving, i.e. if you can solve a problem in a quantum way, you can do it potentially in exponentially faster time than you can do it by classic computation and iteration, right? So the goal with this really is to be able to, come out with functions that can operate in a few different areas. So one that everybody thinks of is cryptography, but it could be other things too, like, for example, financial forecasting, different types of forecasting. There's a lot of use cases for quantum. Haven't even quantified what all those use cases are, but one of the things you absolutely need if you're going to do especially quantum networking is you need a source of being able to generate entangled photons. So basically, I don't know if again, for those that don't know quantum mechanics, one of the things you can do with particles like photons is you can entangle them such that when you create an entangled photon pair, even when they're widely separated, like they can be separated by the distance of the solar system, they can be separated by the distance of the observable universe, a change in one instantaneously causes a change in the other. It's what Einstein called spooky action at a distance. So one of the things that we have done is we've created a chip that generates entangled photons at a high rate, about 10 million photons per second. So this is absolutely fundamentally required if you're going to start doing things like quantum networking. Now, where does this go? If you want to know more about this, there was an awesome session that my friend Tim Seghetti did. This actually happened on Monday, 8 a.m. So you can imagine first thing on Monday, you get up and you're dealing with quantum networking. But you can go and review that in the on-demand library. And with that, we're going to sum up and basically say ASICs to products to solutions to benefits. It all starts with silicon, right? Silicon is just fundamentally important for everything because it's the foundation of everything we do. Does that make sense? And Peter and I are going to stick around for as long as you want to ask us questions. We just might have to take it out in the hall because there will be another session coming in here. But thanks very much. And please fill out your session surveys. It's the only way we make a session better.